This talk is about the structured atom model, or SAM in short. The main theme of SAM is the nucleus of the atom is structured and is directly connected to the properties of the elements and physics phenomena. During this presentation, we will look at the basic rules of the model. Next, we will target several key features or examples of what SAM is able to explain, and close with low-energy nuclear reactions through the eyes of SAM. In SAM, the conventionally known neutron is redefined as a combination of a proton and an electron, or proton-electron pair, PEP for short. It is not fundamental on the same level as the proton and the electron. We reintroduce the electron and with it negative charge back into the nucleus. The inner electrons act as glue that binds the protons together in a fixed structure, based on the rules of spherical dense packing. The nucleus adheres to the concept of spherical dense packing, meaning the nucleus wants to occupy a sphere as small as possible or as many protons in the smallest volume as possible. The denser the packing, the more energy is released. This mechanism at work leads to the shapes shown here from hydrogen on the left to carbon on the right. The growth pattern after carbon changes. The growth starts at two new locations on the initial carbon and repeats the dense packing pattern until carbon is reached again. Larger elements have at its base a combination of multiple icosahedron structures sharing a connecting PEP. As a consequence, the growing nucleus creates a backbone of connected icosahedrons in a fractal pattern. This structure branches, as well as elongates, to prevent colliding branches as long as possible. Because of the positioning of the growth points, the overall structure has an active top side and an inert backside. SAM is strictly based on observations about the atoms and what we know about their properties, such as number of electrons, isotope value, and oxidation states. If an observation does not fit, the model needs to change, not reality. If we follow the basic rules described before, and we take all observations into account, the following atomic nuclei, elements with their isotopes, emerge. As we can see in this animation, from hydrogen to americium. The colors signify repeating patterns, not material changes. All the spheres are protons. Inner electrons are not shown in the animation. Here we see a depiction of the classic periodic table of elements with 3D pictures of the SAM nuclei. And this is the new periodic table of the elements based on SAM with 42 columns in total. Using this approach, we now have multiple empty spaces in the PTE, not unlike Mendeleev's first periodic table, meaning the model predicts configurations that represent new elements still to be discovered. Most of them will be unstable though. At the ICCF-23 conference, we introduced our approach to calculating binding energy with SAM. Here is a short summary. Our calculation is based on the simplest structure which binds something together, namely the deuteron. A single line of connection with a known value of 2.225 MeV. The deuteron is composed of a proton and a PEP, or rather, two protons and an inner electron between them. Each proton touching another proton is counted as one line of connection. By simply adding all the connection lines in the structure and multiplying it with the single line value of 2.225 mega electron volt, we achieve the total binding energy value of a particular element. However, this method does only include the primary organizational patterns of the nucleus. It ignores effects like elongation, branching, shadowing, etc. Since the branching is in competition with the densest packing principle, meaning there is space between the branches of the nucleus, we have to expect that the calculated values will diverge from the actual binding energy. But this is on purpose, because it reveals something profound. This error represents unfulfilled dense packing. It signifies internal stress in the nucleus. It is energy that cannot be converted into binding energy. When the structure is created, it is still stored in the nucleus. Here we have the typical average binding energy per nucleon graph. In blue, the literature values, In yellow, the SAM values. The divergence begins around iron or nickel, where the first branches start to appear. In our opinion, this is the much more useful graph of total binding energies. In blue again, the literature values, in yellow, the calculated SAM values. The vertical difference in binding energy represents the stress energy still stored in the nucleus. It can also be understood as negative binding energy. Even with those differences, the growth patterns of the binding energy still correlate strongly, as we can see in this graph. We want to emphasize that the differences are based on a known error. With more effort, it may be possible to take branching, elongation and shadowing into account, closing the difference. Here is an incomplete list of which questions SAM can answer that current atomic models struggle with. The structure of each element, how isotopes differ structurally from the base element, the base for the cycle of 8 and why it breaks down, the structural base for attributes like oxidation state, the reason for instability after lead, why alpha decay happens, why and how beta decay happens, why there are different decay paths, sometimes with isomeric transition steps, why double beta decay happens, what the reason is for the asymmetric breakup of the nucleus like uranium-235, what the neutron drip line structurally represents, what the reason is behind the increasing neutron-proton ratio in heavier nuclei, etc. The allotted time allows us only to look into a few of those topics in more detail. The main point we want to make here is that all this has a direct causal relationship with the structure of the nucleus. When the question is posed, why do elements become unstable after lead, and is there an island of stability later on? The answer would be, the backbone structure of the nucleus folds in on itself, and branches start to interfere or overlap. This occurs just after lead, and is the reason for the instability of the nucleus. The nucleus also has a growth limit for the same reason, where branches would actually start to intersect or overlap physically. That happens after americium. It also means there is, based on the model, no upcoming island of stability. Next, let's have a look at the typical beta plus decay from fluorine 18 to oxygen 18 and its decay paths. So if we start here with fluorine 19 and remove a PEP or a neutron to reach fluorine 18, there are two options to do that. First, remove one on the right side, leaving just the proton in place. An incoming electron via E-capture converts it in place into a PEP. Second, it is removed from the left side of the nucleus. Then an incoming electron, not an outgoing positron, converts the capping deuteron to the right into two PEPs, releasing 2 times 0.511 MeV. And then one PEP moves over to the left, releasing a gamma ray. The long red line corresponds with the first step on the left, and the two shorter red lines correspond with the second step we see in the structure on the right. In both cases we reach oxygen 18. The two observed decay paths are based on the two options where a PEP can be removed from the fluorine 19 nucleus. The signature 2 times 0.511 MeV gamma rays are in our opinion directly related to the conversion of the deuteron into two PEPs by the addition of an electron. The next example is a typical beta decay from argon-41 to potassium-41. When looking at the structure of argon-40, there are 3 easy options to place a PEP to reach argon-41. These 3 isotopic configurations then decay to potassium-41 by ejecting an electron from the nucleus, thereby converting a PEP or neutron into a proton. Not surprisingly, there are 3 decay paths for this beta decay. In the first case, the 5 ending plus a PEP is converted in place into a lithium structure. In other words, a PEP and a proton create the next deuteron. In the 2 other cases, the PEP first needs to move to the correct ending. This is an isomeric transition. And then it is converted to a proton by ejecting an electron, again creating a deuteron with the existing PEP and converting the 5 ending plus a PEP into a lithium ending. The energetic differences of the isomeric transition steps are related to the varying distances the PEP has to travel on the nucleus. but in the end the difference in binding energy between parent and child isotopes will be dissipated away completely. Next topic will be the asymmetric breakup of heavier nuclei. Looking at the structure of the nucleus, we can identify the two middle branches as stressed entities, which are most likely to break off in case nucleons, like a single pep, are added to them. We also predict the so-called quasi-inner electrons, located between those branches, which will pull those branches together and fuse them when they break off at the backbone base. After adding the pep, the middle branches fuse together and, as a result, break off at the base of the backbone. The remaining backbone represents, after violent resettling, the heavier part of the fission process. The broken off two fused branches provide the lighter fission part, again after violent resettling. This resettling involves radiation, electron emissions, and pep or neutron emissions, which fuel the chain reaction. Looking at the nucleon numbers, we see an exact match for the two peaks in the left figure, related to the nucleons in the remaining backbone structure, which is more or less constant in size. The two middle branches, where growth happens when we step through the actinides, represent the other part. It therefore changes size. This relation is clearly visible in the right figure, and it is expected in the model. We can therefore state that the model neatly explains the asymmetric breakup of heavier nuclei. Looking back at the binding energy graphs, we note that uranium-235 is considerably more stressed than the sum of the stresses of the two fission results. Herein lies the energy release of the fission process. Now we will take a look at SAM and its relation to low-energy nuclear reactions. First, we define the term transmutation. Transmutation is the in-situ change from one element to another. Then, the energy surplus of LENR is, in our opinion, all about the binding energy released in a transmutation step. However, for a transmutation step to happen, the environment must be in the right condition. The environment has to be ionized or plasmified. This can be done through electricity, but other options are possible, such as laser, sound, or massa gas. When and where a discharge happens, either directly through a breakdown of double layers or via a discharge of microplasmoids, transmutations happen. If we look at various historic LENR experiments, we see a pattern emerge. We can have fusion of hydrogen, H+, or deuterons on top of a base material. The result can be stable or unstable. If it is unstable, the nucleus reacts further, even sometimes with a fission step, a breakup of the nucleus. Another option is that we have a direct violent discharge, causing fission events, but also potentially several kinds of small fusion steps. An interesting experiment is Sapphire. What happened in this experiment is, in our opinion, that H+ was fused onto tungsten. The result is an unstable and tungsten with an H+ fission, not unlike uranium, resulting in the same heavier piece of the backbone, namely barium, cerium, lanthanum, and smaller pieces of the branches that were broken off, maybe with a secondary fusion step. Roughly 80 MeV are released per tungsten atom. No wonder the thermal limits of the chamber were challenged during this event. Several speakers of this conference have acknowledged in the past that a theory for LENR is missing. We think that SAM has the potential to be a model upon which a LENR theory can be based. We need to do experiments to check our model, and we hope to play a more active role in the future and are looking for options to perform some experiments we envisioned to test the model. We believe we can predict outcomes based on the input materials down to isotopes being receptive to proton or pep capture or not. Very important are SAM EDEX analysis of involved materials while keeping untouched materials as a reference. We are after transmutations. We think they are at the core of LENR. Another key component is the plasmified environment, which has its own set of effects like strange radiations, EVOs, etc. In effect, we want to build a transmutation machine. So what it could achieve is induce transmutations on purpose in a controlled fashion, therefore also have new elements to work with, such as valuable isotopes, or create new nuclear energy technologies with fusion, find new energy sources, fission of stable elements, or natural decay of artificially created isotopes, and solve the problem of nuclear waste remediation. Concluding, we hope to have given a glimpse into what SAM is about and how it can be helpful. The main concept is that the nuclear structure is directly connected to physics, and that it delivers an actual explanation and visualization for fission processes and other nuclear reactions. We could only touch upon these topics. If you want to know more, you do not have to wait for the next conference. In August, our book, The Nature of the Atom, An Introduction to the Structured Atom Model, should be available through Curtis Press in the UK and on Amazon. Questions?